Welcome to Math GPT. In this video, we build an intuitive picture for two mechanisms that form membrane nanotubes. First, spontaneous tubulation from spontaneous curvature, and second, force-induced tubulation by pulling on the membrane. Start with a small membrane segment of area A. If the spontaneous curvature, called m, is large compared to 1 over the square root of A, the membrane can lower its free energy by making a long tube. On paper, we say, m is much bigger than 1 over square root of A. This tube can appear in three families of shapes. 1. A necklace-like tube, a chain of little spheres connected by necks. 2. A cylindrical tube with constant radius. 3. Unduloids, which smoothly interpolate between necklaces and cylinders. The length scale is set by the spontaneous curvature. The sphere radius is about 1 over absolute m, and the cylinder radius is about 1 over 2 times absolute m. As a concrete value reported in experiments, the spontaneous curvature can be about 1 over 125 nanometers, which implies a cylinder radius of about 62.5 nanometers and a sphere radius of about 125 nanometers. Spontaneous tubulation has been observed without external forces. On supported bilayers, adsorption of antimicrobial peptides can trigger tubes. On giant vesicles, exposing the two leaflets to different polymer solutions also leads to tubulation. In these vesicles, the tubes were observed as in tubes protruding into the interior. For liquid disordered membranes, the tube diameters were below the optical resolution, but theory predicts short tubes are necklace-like and long tubes are cylindrical. There is a predicted shape transition from necklace to cylinder at a critical tube length. Here is the energetic intuition. The main bodies of both shapes can have zero bending energy when their curvatures match the spontaneous curvature. But the cylinder has two end caps, which add a bending energy cost on the order of 2 pi kappa, independent of length. On the other hand, an in-tube has higher volume than a cylinder of the same length, and the osmotic pressure difference compresses the tube, doing volume work that grows in proportion to the tube length. So for short tubes, the end cap bending penalty dominates and necklaces win, but beyond a critical length, the linear volume work wins and cylinders win. A tubulated vesicle stores lots of area in its tubes. This makes the mother vesicle mechanically robust, able to exchange area with the tubes and behave like a liquid droplet with variable surface area. Micropipette aspiration experiments confirm this. The initial suction reveals the spontaneous tension, sigma equals 2 kappa m squared. This sets an intrinsic tension scale for a membrane with bending rigidity kappa and spontaneous curvature m. When the suction exceeds a sigma-dependent threshold, the tubulated vesicle flows into the pipette like a liquid droplet. A second mechanism uses external forces applied locally. Imagine holding a vesicle with a micropipette and pulling a membrane-bound bead using optical tweezers or magnetic tweezers. The pull draws out a thin tether or nanotube. The classical relations are the tube radius equals the square root of kappa over 2 sigma effective, and the pulling force equals 2 pi times the square root of 2 kappa sigma effective. Here, sigma effective is the interfacial tension relevant during pulling. When spontaneous tubulation dominates, it is reasonable to take sigma effective comparable to the spontaneous tension sigma. With a spontaneous curvature around 1 over 125 nanometers, the spontaneous tube radius is about 1 over 2 times absolute m, which is roughly 62.5 nanometers. Summary: spontaneous curvature can drive tubulation into necklaces, cylinders, and unduloids, with a predicted transition from necklace to cylinder at a critical length set by the competition between end cap bending energy and volume work. Tubulated vesicles act as area reservoirs, with an intrinsic spontaneous tension sigma equal to 2 kappa m squared. External pulling can also form tethers with a tube radius and force controlled by bending rigidity and effective tension. Together, these give a unified and testable picture for membrane nanotube formation.